the Math and Physics Resource Center from Saginaw Valley State University online. My name is Amanda, and today we're going to be looking at Math 261, Calculus 3, evaluating triple integrals in cylindrical coordinates. We're going to be looking at the example of computing the triple integral of x dv, where E is the solid region enclosed by the plane z equals 0 and z equals x plus y plus 4, and the cylinder is x squared plus y squared equals 1 and x squared plus y squared equals 4. So using that, we're going to draw the region first, just so we can see it. So if we draw the region in 3D space, we know that x squared plus y squared equals 1 is a circle with radius 1 on the 2D plane, and x squared plus y squared equals 4 is a circle with a radius of 2 on the 2D plane. So we're going to draw that. So here's -1, -2, 1, 2, 1, 2, -1, -2. So if we draw those cylinders in, we're going to have a circle with radius 1, that's going to go up, and a circle with radius 2 right around it. So that's going to go up forever. And the reason why we only stop at the z equals 0 is because we have a plane at z equals 0 that is going to be this bottom plane here that cuts us off on the bottom. So we're only dealing with the positive part of the cylinder that goes until z equals x plus y plus 4, that plane. And that's going to chop through the middle of that cylinder. So now let's set up the triple integral, because now we know we're integrating from this bottom to this top here. And we're going in between this radius to this radius. So when we set up the integral, we know that dv equals r dz dr d theta. And we know that x in cylindrical coordinates is r cosine theta. So now if we set up the integral in cylindrical coordinates, we're going to have x, which in cylindrical coordinates is r cosine theta, times r dz dr d theta. So dz, our z values, we're going from z0, so this bottom plane here, all the way to this plane here. So we're going from z0 to z equals x plus y plus 4, but we're working in cylindrical coordinates. So that means we're going from 0 to x is r cosine theta in cylindrical coordinates. Y is r sine theta in cylindrical coordinates. And 4 is just going to remain 4. Our bounds for dr are going to be 1, because we're only going to 1, the radius here, because we're getting the donut shape. We want just the donut. We don't want the middle. So we're going to go from the first radius, which is 1, to the other radius, which is 2. So we can just get the outside of the donut, not the middle. And then for d theta, this cylinder wraps from y all the way around back to y. So if you do a full circle, that's going to be going from 0 to 2 pi. So now let's integrate this. So now let's integrate this beauty in terms of dz. So first let's take out everything that doesn't have a dz in it and move it to the correct stage that it can fall within. So the r's are going to be in the next step with dr, so we can move them into here. And we can combine them to make r squared. And theta, we're not going to need till we get to d theta, so we can move that over here. So if we rearrange the integral, it's going to look like 0 to 2 pi of cosine theta, the integral from 1 to 2 r squared times that integral, which is going to be from 0 to r cosine theta plus r sine theta plus 4. And that's going to be of dz, dr, d theta. We integrate this in terms of dz, because we got to work our way out. It's just going to be z. And that's going to be from 0 to r cosine theta plus r sine theta plus 4. And with all our other fun stuff. All right, so now that we have that, we know z is going to evaluate to be r cosine theta plus r sine theta plus 4, and that's going to be minus 0. So our new integral is going to look like 0 to 2 pi cosine theta of 1 to 2 r squared times r cosine theta plus r sine theta plus 4. And that's going to be still dr d theta. So now we're going to have to integrate this in terms of r, while treating theta like a constant. So first let's distribute the r squared. So we're going to have r cubed cosine theta plus r cubed sine theta plus 4r squared. So now let's take the integral. So now taking the integral in terms of dr, it's going to come out to be r to the 4th divided by 4 cosine theta, because again, theta is being treated like a constant. R to the 4th over 4 plus, well, times sine theta, and that's going to be plus 4/3 r cubed. And that's going to be from 1 to 2. And don't forget, we still are d theta, and we still have that beautiful integral from 0 to 2 pi of cosine theta. And now we're going to evaluate from 1 to 2. So to evaluate from 1 to 2, we're going to plug in 2 to the 4th over 4 cosine theta plus 2 to the 4th over 4 sine theta plus 4/3 2 cubed. And then that's going to be minus 1/4 cosine theta minus 1/4 sine theta minus 4/3. And that is still going to have those outer dimensions. All right, so now we're going to simplify all this. And then it's going to come out to be going to end up being 15 over 4 cosine theta plus 15 over 4 sine theta. And that's going to be plus plus 28/3. So now we're going to integrate this with our cosine theta. So now we're going to multiply that cosine theta in there. Multiply it by everything. And we're going to break that up into 3 new integrals. So we're going to have from 0 to 2 pi of 15 over 4 cosine squared theta. And we're going to have that plus from 0 to 2 pi of 15 over 4 sine theta cosine theta d theta. And that final integral is going to be from 0 to 2 pi 28 thirds cosine theta d theta. So now we're going to solve out each integral. For the first integral, to solve it out, we're going to have to use a trig identity. The trig identity that cosine squared theta equals 1/2 plus 1/2 cosine 2 theta. So using this identity, we're going to get the new integral 0 to 2 pi of 15 over 4 1/2 plus 1/2 cosine 2 theta d theta. So now we're going to take the antiderivative of this. So 15 over 4, it's going to be times 1/2 theta plus 1/4 sine 2 theta. And that's going to be from 0 to 2 pi. So we're going to have 1/2 times 2 pi. And that's going to be plus 1/4 sine of 2 times 2 pi, which is sine of 4 pi, which is 0. And that's going to be minus 1/2 times 0, which is 0. And that's going to be minus 1/4 sine of 2 theta, 0, which is, again, 0. So the first integral comes out to be 15 over 4 pi. So now the second integral, we need to do a u substitution. So with this u substitution, we're going to have u equal to sine theta and du equal to cosine theta d theta, which will give us the new integral. It's going to be with the new bounds. It's going to be sine of 0, which is 0, and sine of 2 pi, which is 0, of 15 over 4 u du. But if the bounds are from 0 to 0, therefore the whole integral is 0. The last integral we're going to solve out for is this one right here. And that's going to be 28 over 3 cosine theta. So that's going to come out to be 28 over 3 times sine theta. That's going to be from 0 to 2 pi. Well, we already looked at the other cases, and it's going to come out to 0 because sine of 2 pi is 0 and sine of 0 is also 0. So we're going to end up with 0 minus 0 times 28 over 3, which makes no difference. So this all comes out to be 0 as well. So our final answer is 15 over 4 pi. Thank you for watching this video from the Math and Physics Resource Center from Saginaw Valley State University.